Hey physicists, so we just finished looking at line density and we're moving into center of mass now. So the center of mass we've studied a little bit at the beginning of the year. Remember when we started doing force diagrams, we said if we're going to condense this object all the way down into this one point that will be representative of that object, we're going to call that the center of mass, and all of the forces will come out of that mass for then. So the center of mass then we're going to define as the point of an object at which all the mass of the object is thought to be concentrated, or the average location of the mass. Now, sometimes that mass does not need to be actually in the object. If you think of the pole vaulter here, the pole vaulter has all of this mass here. The mass of the center of mass is going to be somewhere in in that empty space underneath the pole vaulter. You can also think of something that be like a donut. The center of mass of the donut is not going to be in the donut itself. It's going to be in the very center, in the hole. And as my father-in-law, who is Irish, says, as you wander through life, what will be your goal? To keep the eye upon the donut and not upon the hole. Just a little bit of Irish blessing there for you. So you could think too, as our solar system, between two different planets, the center of mass, like the center of mass between the moon and the earth, could potentially be outside of the center, outside of the mass of the earth. Or if we're looking at the sun and the earth, the center of mass of the sun and the earth is going to be somewhere in the sun, but not at the very center of the sun, because that center of mass gets displaced off of the center there. Or the center of mass of the entire solar system, it's still well within the sun itself, but it is not in the sun part of it. And so that's what causes the sun to kind of wobble on its axis. And sometimes whenever we're looking at stars really, really, really far out in the galaxy, we can tell if there are planets on it because there's a wobble in the star, because the center of mass is not in the exact center of the star itself. So think through, here are some equations that may have looked familiar to you. So Newton's second law, F equals ma, force equals mass times acceleration. Well, then when we got into momentum, we studied this equation that says momentum is mass times velocity. So wouldn't it kind of make sense that there would be something that is a mass times position? And that's really what our center of mass is. It's the center of mass represents that position. So we can say when we're looking at point masses, or think of it as like planets, for a point mass, we add up all of the center of masses. So I'm going to say that the total center of mass, or total position, times the total mass is equal to the sum of all of the individual masses and positions. So m1 x1 plus m2 x2 plus m3 x3, and so on and so forth, where mi is the mass of each of the different particles, xi is the position of each of those different particles, and then uppercase M is going to be the total mass of all of the particles together. So, for example, find the center of mass of a system of 4 particles that has a mass of 2 kilograms each. So I have 2 kilograms, and then each are located these 3 centimeters, 5 centimeters, -4 centimeters, and -2 centimeters if this is my origin of 0. So think through then. If you remember, we said that the center of mass, xcm, times the total mass is going to equal the sum of all of the xm's, right? So I can look at that and say, well, if each of these were a mass of 2, 2, 2, and 2, I'm going to say 2 times a -4 mass times position. So negative because I'm going to the left there, plus 2 times a -2, plus 2 times a +3, plus 2 times a +5. And that's going to give me -8, -4, +6, +10. Make sure, just double check myself that I did this right. -8, -4, which is going to be a -12. And that's going to then give me -12, +16 is going to be a +4. And then I'm going to have on the other side 4 times 2, or in essence 2 plus 2 plus 2, 2 plus 2 plus 2 plus 2, and xcm. And then that xcm is that's going to be 8. Divide that over, and I'm going to get a half of a centimeter. So my center of mass is going to be somewhere right here at about a half. Now, a couple different things that you may have noticed. Notice that I kept these in centimeters. I don't necessarily need to convert those as long as all of them are in the same thing. The second thing is, notice that I wouldn't have necessarily had to have used this 0 line as my reference. I could have picked this to be my reference. If I do that, then let's see if I can change my pen color here fairly quickly. If I do that, then I'm going to end up with a 0 times 2 for my first one, plus a 2 times a positive 2. So I'm moving this way now, positive 2. Plus a 2 times, now this is going to be 2 plus, let's see, 2 plus 2 plus 3 is going to be 2, 4, 7, right? And then this other one over here is going to be plus another 2, or 5 plus 4 is going to be 9. So 2 times 9 is going to equal the x center of mass times the total mass again, which is 8. So this will be canceled out. This is going to be 4 plus 14 plus 2 times 9 is 18. So this will be 32, 36. 36 equals 8 xcm. And when I do that, 36 divided by 8 is going to give me an xcm of 4.5 centimeters. And notice that that value is still 4.5 centimeters. So whenever we do this, our answer is going to be in reference to wherever we put the 0 line. Moving on, there's our answer, and it looks like my original, when I calculated it, I went with this origin as the reference. It's also important to note that this works in 2 dimensions, so find the center of mass of the following system. So what I'm going to do then is say that this is 2 meters away. These are 2 meters away. So what I want to do, let's start in the x dimension and say the x center of mass, I want to know how far left and right. So what it would do is it would be advantageous for me to do what we said earlier. If I make my origin here, then can't I say my x center of mass times my total mass is going to be equal to 0 times both of those, which means that's going to go away. And then I can literally just do the 3 kilograms times the 2. And over here for my total mass, I'm going to have 1 plus 2 plus 3, which is going to be 6. So this is going to be xcm. So my x center of mass is going to be 1 meter. Now, doesn't it make sense that if I literally just were to combine this 1 and 2 together and I have a 3 and a 3, wouldn't it make sense that my center of mass is going to be exactly halfway through that in the x point there? Now, let's look at the y direction. In the y direction, wouldn't it make sense for me to make the 0 line for my y be my origin? Because then I can say the x center of mass times the total mass, which we already calculated as 6, is going to equal this 1 guy up here times 2. And so my center of mass is going to be equal to a half, or 3, I'm sorry, not a half, it'll be a third, right? 2 divided by 6, so 0.333 repeating meters, which is going to be somewhere like, if this is half, a third might be here. So the center of mass is there. And again, wouldn't it make sense that if I have 5 of my values lower and only 1 of them higher, the center of mass of that is going to be closer to the lower values where there's more of it there, and that's where that 0.33. So I would say that my center of mass of the whole system, and I put this shouldn't be an x, this should be a y and a y, is going to be the combination of those 2 values. And if you look and see there, it looks like we calculated that correctly. Okay, moving on. So how would you find the center of mass for a rod? So the last ones that we did were point masses. Whenever we want to look at a rod, then our rod is not going to be a single point mass. So we have to look at this and say, hey, there's got to be some other way to look at it. Well, if I do the center of mass is equal to the sum of all of the individual masses, isn't the sum just another way to express an integral? So this is going to end up being in integral form. The center of mass times the total mass is the integral of the position with respect to the changing mass as you're moving across that rod. Hey, doesn't that look familiar? Like maybe that's why we had to study linear density earlier in order to solve this one, and why that's sort of a crucial value that we get that. Now notice again too that I did this in each of the different dimensions. So we have an x dimension, a y dimension, a z dimension. If you haven't learned anything yet, one of the things you should remember is that in each dimension we have a different problem. Remember that we're usually solving for the position, so we'll divide the total mass over each of those different ones. And then the center of mass can be found in all of the dimensions. And we can talk about this in terms of I, J, and K, which is typically our X, Y, and Z for what we're dealing with. So let's say that we have a uniform density rod. So it means the density is not changing. So a rod's mass density is constant over the length of the rod. Then couldn't we look at that and say the density of the rod is going to be the total mass divided by the total length of the rod? Oh, if only we had a way to relate XDM. And oh yes, that's what we talked about in the line density equations, right? So when we look at since this is a constant density, we can integrate that total mass as the integral of the line density with respect to position. We're going to integrate that y lambda. Remember, lambda is constant, so we pull that out. We're going to integrate it from 0 to L. So we'll say that the beginning of the rod is here at 0. The end of the rod here is at L. And when we integrate that, we get that the total mass is equal to the line density divided by the length of the rod. Oh my goodness, doesn't that make sense? Because that's what we just wrote up there at the top, right? So then we can take and plug that into the center of mass equation. And so we say the center of mass is the total mass, which we just found, which is equal to the integral of x dm. And remember that our dm value is really this lambda dx, right? So if I take this guy here and solve for dm, then I'm going to say that dm is equal to lambda dx. So on the left side of the equation, I can plug in this lambda L value for my M, and on the right side of the equation, I can plug in this lambda dx for my dm. So when I go to integrate that, then I'm going to integrate, I can pull my lambda out because it's constant. I can take my x value and integrate it, so x squared, pull down the half, and take that from 0 to L. Then I'm going to have 1/2 L squared lambda on the right. I'm going to plug in this, like we said, this lambda L over here. And when we cancel out our like terms on each side, then we have that the center of mass is 1/2 the length of the rod. Now, conceptually, doesn't that make sense too? That if I have a rod, so picture my pencil as being just a dowel rod, and it has an equal density over the entire length of the pencil, then shouldn't I be able to balance that at the very center of the rod because there's an equal amount of mass on each side of those? And that's what a uniform density rod would be. Now, a rod's mass changes according to the following equation. So let's make this a little more complicated. So maybe this is something like a baseball bat, or maybe it's a cone where the cone gets bigger and bigger and bigger on one end, or has more mass on the other, only it doesn't look like a cone. It's just that it gets heavier the further along we get. So this is some constant alpha. Maybe it's like a 4 or a 2 or a 1, just some constant value. We're going to leave it as a variable. So remember that our center of mass times the total mass is equal to the integral of the x dm. We can say that the lambda is dm over dx. That's our change in mass over our change in length. If I solve for dm, I'm going to get dm as lambda dx. And then I can find my total mass by saying that it's the integral of the lambda equation with respect to x. Remember that. So we integrate both sides here. This is our line density problems. So I'm going to plug in my lambda value here, plug that in down here, and then I'm going to integrate. So the integral of that, I can pull out that alpha value because it's a constant. Integrate x, I'm going to say that that's x squared times 1/2 times that constant. And we're going to integrate it from 0 to L, so it's a definite integral. And that means that I can plug that value in and get a total mass there of 1/2 of that constant times the length squared, right? Now, nextly, we're going to take, that's the first half of the problem, is the line density. And that's why we did that as a separate unit earlier, or lesson earlier. Now we're going to take and put that into the second half of the part, which is the center of mass. So I can take this integral of x dm. Now remember that that dm value is this lambda dx, so I can plug that in over here. And then I'm going to integrate that. Again, I can pull out the alpha because the alpha is a constant. I end up with an x. Oh, that's interesting. So I messed that up. So I have an x squared. Then I'm going to integrate that. So this should actually be x cubed. No, that's right. So I have an x squared. I'm going to integrate that, which is going to end up being 1/3 x cubed, but I'm going to take it from 0 to the length, and that's where I end up getting this 1/3 L cubed, and then I can put my alpha back in there. Now, this on this side is the left side of the equation where I'm going to take my answer to my mass total and plug that in for there. Again, I can cancel out like terms, cancel out the alphas, cancel out the L cubes, L squared, and I end up with this XCM. I kind of jumped a few steps here. XCM, if I multiply both sides by 2, and I end up 2/3 of the length of the rod. The math is correct there, so if you need to, pause the video and sort of check through my math just to make sure that you followed what I did there. Again, now doesn't it make sense that if this has a constant increase in mass across the rod, that somewhere around 2/3 of the rod, this heavier end is going to balance out with the other 2/3 of the rod on that rod, because that's where our center of mass would be. Okay. Moving on, so the center of mass of symmetrical objects, try and make this easy on yourself. So a lot of times this will show up as a free response, or not free response, as a multiple choice question, and you can easily eyeball it to say, yeah, that can't be right. So for instance, here's an old multiple choice question that shows up all the time. The diagram below shows a U-shaped bar made out of a uniform material. Where would the center of mass be? Now, it doesn't ask you at all where the center of mass would be in the x direction. You know that because of the symmetry of the object in the x direction, it's got to be straight down the middle. Now, whenever we look at this and we say the symmetry in the y direction, if there was another part of it here, then wouldn't C have been our answer, because it would be symmetrical in the y direction. But there isn't another rod there, which means that there's no mass on this side to balance out this side. So then wouldn't our answer have to be B? Because it would pull the center of mass towards where more of the mass is. It can't be A, because there's no mass up here balancing out the mass down here to pull it up towards the A direction. And in the same way, it can't be D, because there's no mass down here pulling this mass down, and that's why our answer has to be B. Okay, moving on. Position, velocity, and acceleration of the center of mass. We can use this to our advantage to do the same thing where we have the position is this change in mass. So think if I multiply the sum over to the other side, I have center of mass times mass. This is the sum of the mass times the position. I can do the same thing where this is going to become the velocity and velocity, because if I dt both sides, dt, then that's going to give me my velocity. And then the same thing, if I dt my velocity, I get my acceleration, and that will help give me the velocity of the center of mass, or the acceleration of the center of mass. And that's where we end up getting those values that we talked about earlier. Uniform piece of sheet metal shaped as shown below. Compute the x and y coordinates of the center of mass. Again, let's make this easy on ourselves. So what I'm going to do is I'm going to put my center here. Maybe I need to change colors here to make this a little easier to see. I'm going to put my center here, because if I do that, then doesn't that cancel out the center of masses of these 3 blocks in the directions that I'm looking at? Now, it does make it a little bit more complicated, because we'll have to make sure that we use the right distances when we do that. But I can say that the x center of mass times the total mass, and in this case, it doesn't give us a mass of the block, so I'm just going to make one block equals 1 mass. So 1, 2, 3, 4, 5, 6. So the total center of mass times the total mass, which is 6, is going to equal the sum of all of the individual ones in the x direction. So these all cancel out. I'm going to have 2 of the blocks that are going to be at what we would say is 10 centimeters away from that. And I'm going to have 1 block that is going to be what we would say is 10, 20 centimeters away from that. And so when I take and do that, I'm going to end up with 20 plus 20 divided by 6, which is going to be 40 divided by 6. And notice that we end up with a center of mass of 6.67 repeating, or 6.6 repeating, and that is going to be in centimeters, right? Now, that doesn't match my answer, but remember I shifted off my origin by 5 centimeters. So when I go ahead and add the 5 centimeters to that, I get 11.6 repeating centimeters, and that's where my answer comes from. Again, we can do the same thing where we talk about this in the y direction. So I'm going to say the y center of mass times the total mass, which is 6 again, 1, 2, 3, 4, 5, 6. And in the y direction, I'm going to cancel out all of these, will become 0. So I'm going to have one mass here that is 10 centimeters up, and I'm going to have plus 2 masses that are 20 centimeters up. So 20 times 2, 40, plus 10 is 50. So 50 divided by 6 is going to give me a value of 8.3 repeating centimeters. And again, remember we shifted this up by 5, so I'm going to add another 5 centimeters to that, and that's going to give me a value of 13.3 repeating centimeters. And lastly, here comes the really, really fun one. So let's say where we have a line density that changes by an equation. Now it's exactly the same thing, it just becomes more math for us. So again, we're going to say that the line density is equal to the change in mass over the change in position. To find that total mass, I'm going to integrate both sides of that. But now I'm going to have to plug in for this lambda value the equation that we have up here. So I plug in the equation, I integrate x squared half times 7, x times 12, and that's going to be from L to 0. So my total mass is going to be 7 halves L squared plus L plus 12L. So that's the first step, is the line density. Second verse, same as the first. So I'm going to take and do the center of mass times the total mass is equal to the integral of x dm. Now remember that x dm, when I solve for dm here, is going to be lambda dx, and that's where we get this value over here. But instead of being able to take that lambda value, now again, I have to take this and substitute it in for lambda. Frickers. So I'm going to substitute, so I'm going to manually chug through the rest of this, right? So the x center of mass times the total mass is going to be the equal of x, the integral of x times 7x plus 12 dx, which is going to be the integral of 7x squared plus 12x dx. So my x center of mass times the total mass is going to be, let's see, x cubed 7/3, right? Plus x squared, 12 divided by 2 is going to be 6. And this is going to be from 0 to L, which is going to give me 7/3 L, 7/3 L cubed plus 6L L squared. Now on the right side, I'm going to resubstitute my m back in and say the x center of mass is 7 halves L squared plus 12L equals 7/3 L cubed plus 6L squared. And boy, isn't this fun. So now I'm going to divide both sides by my total mass here. And let's see, x center of mass. What it looks like to me initially is I can cancel out an L to make this easier, right? So this L will go away, this L will go away, this will become squared, and this will become just a regular L. So then I'm going to have 7/3 L squared. How about we pull an L out of that one? So L times 7/3 L plus 6 all over 7 halves L plus 12. And for now, we're just going to leave it like that. If you saw this on an AP test, which you probably wouldn't, then they would make this so typically something will cancel out here, or you'd be able to simplify it more. And if they don't, then you would just leave it like that. The center of mass of the rod is going to be at that spot. So major ideas. Remember that center of mass is if we were to condense all of the mass down into one point. Where is that one point? That the center of mass is going to be a position. And the way we would calculate that is take that position times the total mass, and that's going to equal the sum of all of the individual masses. If it's a point mass, you can do xm plus xm plus xm plus xm. If it's a rod or some other solid object, you're going to do this integral of x dm. Then if you're doing the integrals, you're going to take and do the line density that we studied earlier, solve for the total mass, and you're going to use that line density that we studied earlier to plug in over here for the equation to do the integral value of that. Yep, and that's going to be center of mass in a nutshell.